Hello.
Yes, sir. Yes, sir.
Hi. Yeah, so I see people are joining slowly. Yeah, so tell me, so how is it going? So did you guys all like the uh, this tutorial on Saturday? Did you find it fast or did you find it kind of not exciting or
Yes,
what did you find?
It was fine.
It was fine. Okay, so you guys now therefore have some good and some understanding of what the usage of the graphs is, right?
So,
Okay, so before I start doing anything, so yeah, so tell me what all in any doubts that you have, or what all doubts you have from whatever has been done so far in the class or in from the tutorial. But, what about the assignments? No doubts about the assignments. Uh, okay, so in that case,
sir, I have a doubt in problem set, asymptotic and recurrence one,
yeah,
and D part of fifth question.
be part of the fifth question. Now I have to find out where what is that question. Let me just quickly try to find out. Just one second. The D part of the fifth question. Right. Right. Okay. So Tn equals to 2t log n plus n. Right. Good. So see. First of all, as I told you earlier, you don't have to necessarily find the exact value over here. Okay. That is first thing. Second thing is that you have to kind of try to see what is the best you can try to get from here. So so maybe I will share my screen. Do you see my screen?
yes, sir.
So you have T of n equals to 2t log n plus n. Now, what do you think this is? Is it an exponentially growing? Is it a polynomially growing? Is it a linearly growing and what? Okay. So first of all, one thing to notice is okay, we might want to expand it once more or something. So what if I expand it once more? What will happen? It will get 4t log n, right? Plus 2 log n plus n. The main idea is that see, this is log n, this is n, and this is log n. Log n is way smaller than n. This is n and this is log n, right? Log n is way smaller than n, right? So you know that, for example, one thing that you know is that n plus n over 2 plus n over 4 plus dot dot dot, dot is equals to twice n, right? In fact, if you make this n plus something much smaller than that, right? If you have n plus say n by log n plus n by log square n, it is actually just nothing but asymptotically equal to n, because this quantity is a very slow moving object. So this is basically, this n will dominate the everything. Everything else will be very small. So now here I have log n, which is even smaller than n by log n.
Do you mean like multiplying by log n rather than dividing?
No, divided by log n.
But
See,
like
n
if
plus n by 2 plus n by 4 plus n by 8, what is that?
Sir, log square n is applying or squaring the value of log.
Sorry?
Log square n, are we applying log twice or are we?
We are going to apply log twice, right? Here?
Right, so in the summation we have written log square n.
No. Let's yeah. I mean, I'm not, so just think, say, look at this one, okay? For now, I'm just written log square n only. Okay? I've written log square n only. But what I'm trying to say is that, log n, so this log n is way smaller than n by log n, this term. And what you will get is that log n is way smaller than n by log square n. Okay, in fact, if you apply log some k times, you see that this is way smaller than n to the power log, I don't know, 2kn or something. And this is the kind of things that I want you guys to kind of realize, that when you apply log, you have something, when you apply log, it's a very fast decreasing object. Okay, so so that means if this adds up to at most n, okay, asymptotically equals to n, then this quantity cannot be more than n, right? And this is of course more than n, you know that. So one thing that I can clearly conjecture, and which is the correct thing, that T of n is asymptotically equals to n. Now you can try to prove this. Okay. And that you can either, yeah, so basically Tn by n. So what do we have to do? You have to prove that limit of Tn by n goes to 1. Okay. And you can try to prove it in various ways. But more importantly, for your purpose, what I want you guys to think of it more is that instead of trying to prove it in formally, you should first be able to identify what is the quantity T of n. And the main idea is that this log n is a super fast decreasing object. Okay, so n plus log n plus log n plus whatever you apply, that is nowhere close to even this quantity. So what you will have is this object. Is the intuition clear?
Sir, can you again explain the second equation, the n plus n by log n?
Okay.
I wasn't present during that time.
Okay, so I am just saying is that if you have n plus n by 2 plus n by 4 plus everything, it is twice n. You know that, right?
Yes, sir.
And you also can see that n plus n by log n plus n by log square n plus everything is actually asymptotically equal to n. Okay, you do the calculation. You know how to do this calculation, right? This is n into 1 plus log n plus 1 plus log square n plus 1 plus log cube n and so on and so forth, right? What is this object? And that object, you will see that this actually, as n goes to infinity, this goes to 1. I mean, this by n is actually goes to 1.
Here the log square is the square of log n or the log over log n?
Now, log square n, log n whole square.
Oh,
Okay. First of all, the log square, log of, I mean, this is just a GP series.
yeah.
Okay. But now this one, when you have a recurrence like this, you have a n plus 2 log n plus whatever 4 log to the log n plus 8 log n and so on and so forth, right? Now individual term wise, I want to claim that this, see, the log n is a way smaller term than n log n, n by log n. Log n is a way smaller term than n by log square n. The log n is way smaller than log by n by log to the power kn, or log n whole to the power k. So individual term wise, this summation is a smaller summation than this summation, right?
Oh, okay, I got it.
And so if this one itself is like something like n plus small o of 1 kind of stuff like that, right? So this must also be n plus small o of 1 kind of stuff.
N plus, oh,
Okay.
acha, okay.
So this is another way of writing it, is that this summation is n plus small o of 1. Meaning, what does it mean? N plus small o of 1? That means divided by n, this goes to 1. Right? What is the small o of 1? That means that divided by,
Constant.
yeah, actually small o of n. I don't need a small o of 1. N plus small o of n. Right? Because so that if you divide it by n, you get 1 plus small o of n by n, which goes to 0. So it will be limit of this object by n is goes to 1. So maybe this is something, another thing that I want to write. So this is same as T of n equals to n plus small o of n. Okay. So in other words, this is something that is basically n. N is the main thing. It doesn't even have a, any constant over here. Okay, it is just n, pure n, not even constant times n, not even theta n. It is just n plus something that is much smaller than n. So are you guys confused with this particular thing?
No, sir.
If you are, you should take this one as an exercise. Prove that this is the case. In this case, for anything, okay? For any function, if T of n is asymptotically equal to n, that means T of n equals to n plus small o of n. Okay, is it clear? Okay. Any more questions? Any questions?
So I had a doubt regarding the assignment.
Yeah.
So in the fifth question, it was asked to write the algorithm for defining a heap from an array,
Yes.
and it said that it should also support addition, insertion, deletion, etc.
Yes.
So should we write algorithms for all these two?
You should write an algorithm for this too. Yeah. I mean, if you have been told where is that element, then how do you delete that element and yet maintain the heap? structure. And if I give you an element and I ask you to add it to the heap, how do you do that? This you should give the algorithm for this. I mean, the algorithm has been described intuitively in the class or in the
Yes,
video rather.
yes, sir.
So you have to write the pseudocode of it.
Yeah.
Okay.
Sir, in the third question of the assignment, the time should be order of n, and that is average case runtime or
Now I forgot what is that.
as assignment 2.
Two, right? Third question. Where is the element? No, this is worst case. This is worst case.
Oh, okay. Sir.
So while proving time complexity, so we are getting some recursive relations which we have
Okay.
already solved in the given problem set.
Yeah.
So do we need to solve them
No,
again?
it's okay. You can just. It's okay. I mean, if you have a recursion and that recursion is kind of, I mean, it's kind of clear what the recursion is, you can write it.
It's actually exactly the same as what's given in the problem set.
No, then you can of course write.
Sir, in question 5C, what do we have to do? I am not understanding.
It is
because-
exactly the same as deleting. Okay, in the deleting of an element, okay, basically you have been given a heap and you are uh, told which element that you have to remove. Okay, you have been given an address to that element like this, and you have to remove that element. Okay, in the case of the third question, it is just says that okay, delete the minimum in the heap. That's it.
But if it's a mean heap, we know that minimum is the first element.
Exactly. So you just have to delete the first element, and you have somehow ensure that. So it is like the same thing as the deleting the element in a heap.
Sir, here we are told that we just have to extract the minimum element. This means that we don't have to maintain the heap structure after extracting that
You
element.
have to maintain the heap structure. Okay. So in a normally in a heap thing, okay, there is a, I mean, if you have read the things in some other book and something, there is the extract mean is actually the main thing that they do. You extract a mean and maintain the heap structure. Okay, and then there is the addition. The deletion is not something that is done in the heap structure, because deletion can only be done if you have been given an address to that element that you have removed. So I just gave it to you guys just as a kind of an exercise. It's exactly same as the extract mean. Okay, so you have to always, whenever in a heap, you have to delete or add or do whatever you want. You have to at the end maintain the heap structure. Okay. Hello.
Sir, the algorithms we know, so we have known so far, the worst case is always greater than n log n, order of n log n, and and runtime is order of n for or counting sort, maybe bucket sort in
Right.
per suitably chosen k.
Right.
So, but worst case, for the worst case, in the third problem,
Yes. See, the third problem, you have been given that the elements are coming from a particular range. Okay, it's not a completely general setup, right? It is coming from a particular range, and that is exactly what you have to use. Something like bucket sort or something like, yeah,
But
think
sir,
of it, counting sort.
average case is order of n is possible, I know, but worst case,
Worst
I
case for
mean,
counting sort is our order of n, right?
but they are order of n plus r, and
They're not. So that means that R is coming out for something, right? So here R is in Q, so it's not good. But think about it. You can do it.
okay,
Okay. So you have to use the fact that the range is coming from 0 to n cube minus.
okay.
Okay. You have to somehow use that fact that the range is. So even if you cannot, say if I give you and you cannot solve the worst case, if you can give me an average case, that's also good enough. I mean, I'm not good enough meaning that'll be, I mean, that will be something nice. Yeah. Okay. So some more questions still still up to sorting. No problem. No questions from sorting or assignment or this thing. Okay. So now let me stop my share, and I want to ask a polling question. Now this is important. I had asked you to read some chapters from the Kleinberg Tardos book. I don't know how many of you have read it. So I want to ask you this question. Okay, so the chapter that was there was 4.1, 4.2, 4.3, 4.4, and 4.5. And I want you guys to answer which of them have you read. Oh, maybe I made a mistake. Just one
The
second.
single choice.
Okay, just one second. Just one second. I mean, I will just one second. I made a mistake. Yeah, it's made a single choice. Sorry. Yeah, if you are interested, you can look at the, you can check your this Kleinberg Tardos book about which chapters have you read or not read. Okay, I'm launching a new poll. Yeah. Good. I'm actually impressed with you guys. So almost, so I don't know. So there are 30. Yeah, only 25 people have has kind of given their answers. Okay, so basically what I see is that almost everybody has read the section 4.1. So that's good. So you have any questions on section 4.1? Nobody has any questions on section 4.1? Excellent. And quite a lot of people have read 4.2. So that's also very good. So you guys got some ideas about the greedy algorithm, right? Okay. Yeah, any questions? No questions so far? Okay. Hello. Am I audible?
Yes, sir.
Okay, so if you have seen the section 4.1 and 4.2, okay, and some of you have seen 4.3 also. So I would first of all ask you guys, whoever has read it and all, to start maybe trying out some exercises from 4.1, 4.2. And if you have any doubts, please ask me or ask me anytime. That's not a problem. Okay. And so today what I will be doing is mostly from the stuff for 4.4. I will just quickly go over it a little bit. So that is where the uh, uh, reachability in graphs is looked at. By the way, what I understood from talking to Santon, who gave this presentation on Saturday, is that many of you guys are not completely aware of uh, some uh, some certain properties of graphs. Am I so in if I use, or if at any point of time we are using some notions of graph that you are not comfortable with, or you have not seen it in your discrete math course, please stop me and ask me immediately. I will be happy to go over it as much as possible. Okay. So if, for example, you guys are not familiar with the planar graphs, right?
No, yes, sir.
Huh? Hello?
We didn't know
Ye-
about them.
You did not know all planar graphs. Okay. I mean, okay. So planar graphs, I don't think we will need it as such, but I will give you a possibly a small write up or maybe a small video on planar graphs that will kind of help you guys to, because it's a very beautiful concept. So for example, like you guys read 4.1, right? Section 4.1. And section 4.1, you had these intervals, right? And so you had, so maybe forget this. So you had these intervals, right? And you were trying to look at how to kind of how to have as many intervals as you can which are disjoint, right? So you can define something called an interval graph. What is the interval graph? An interval graph is basically you have the vertices are the intervals. So so maybe if I forget that. So what all things you have? You have the intervals, say I1, which is S1, F1, right? I2, S2, F2, and like that till I maybe T, which is STFT. So you can define a set of vertices which are basically the set I1 to IT, and you have an edges such that, say, there is an edge between II and IJ if and only if these two intervals intersect. II intersection IJ is non-empty, right? And so this is called an interval graph. And what were you actually finding there? Your goal was to find a set of intervals, right? Say you will say, oh, say I will take this interval and this interval and some other interval, such that these intervals don't intersect, right? So if you want to find a, so your goal was to find a set of intervals that don't intersect. So what does it mean in this language of graphs? Can somebody say?
Find the number of components in graph.
No, 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 no. Not finding number of components in graph.
Non-adjacent vertices.
Okay, so okay, what is the component? Okay, maybe you guys have missing this terminology of component. What is the component? So if I have a graph, say like this, okay, so I have a graph like this, right? This graph might be connected or not connected, but this graph has two components. So this is one component, this is another component. Components are disjoint or disconnected set of vertices basically. So this is one component, which is it's a connected set of vertices, and this is the another component. Okay, meaning there is no path from this vertex to this vertex. Okay, so this is components. Okay, now this is not what I'm interested in. If I have such a graph, I am happy to have this vertex. If this vertex is a interval, right? I know that this vertex intersects with this vertex and this vertex. So these two intervals cannot be scheduled. But this interval is not adjacent to this interval. That means if I choose this interval, I can also choose this interval. And if I choose this interval, I can also possibly choose this interval. Right?
So the complement of the graph.
Number of, no, sorry, I don't get you. Complement of the graph is completely different. Complement of the graph is the things that are not there. So if I use a different color, so complement of the graph is basically this blue, this purple edges that are not.
Click size in component of graph.
Hmm?
Maximum click size in complement of graph.
Maximum click size in the component of graph, the complement of graph. Let me see. Okay, I mean that might be possible. That is possibly right. But okay, so there is a bit more. Instead of going to complement, you can
don't know
stay
what
with.
that means.
Huh?
Like most of us don't know what that means.
Oh, most of us don't know what a clique is.
No, sir.
Oh, okay. Okay. You know what a complement is?
Yes, sir.
Yes.
Okay. I mean, complement of a graph is, right?
Yes.
Okay. So forget clique. Don't worry about cliques at this moment. Okay. So don't worry. But let's just think about it. So I am saying that you could have chosen this 3. This is the possible things, right? These 3 intervals. So interval 1 I can choose. I cannot choose interval 2. I cannot choose interval 3. I can choose interval 4 because interval 4 and interval 1 is not adjacent or not intersecting. I can choose interval 5. I can choose interval 6. I can choose interval 7. Right? So this is a possible set of intervals that I could have chosen. Okay. Or the other option would have been, what happens if I had chosen interval 3? In that case, would I have chosen interval 1?
No.
No, because interval 1 intersects. The fact that there is an edge here, note that the edge is there only when there is an intersection, right? That means the fact that that there is an edge here, it means that if I choose this edge, this vertex, I cannot choose this vertex because this has an intersection. Similarly, if I choose this vertex, I cannot choose this vertex. Yeah.
Do we want to find the complete subgraph of the complement of this graph?
No. Forget the complement. Let's go for this normal graph. So what do we want? Can somebody actually say in the case of this graph, forget the complement. When is forget the finding the maximum set of intervals, but what is it that we want? Forget the maximum. But I want a set of intervals such that they don't intersect, right?
Sir,
Sir, if we think in terms of chromatic number, then we can say that subset can be colored using the same color.
Right, you are right. Maybe that is one way of saying it. But even simply, what is it that we want? We want a subset of the vertices such that such that for all ij in the set S, ij is not in the H set. Okay, this is a very basic translation to this to the language of graphs. Am I clear here? Hello?
Yes, sir.
Yes, sir.
Okay, there's no issues. I've just converted this definition in English to definition in graphs. Okay. Now, such a set. Okay, so here I will use such a set is called. Now, this is very important. Okay, this is one of these. This is something that we will be use it later on also. It's called an independent set. Okay, if you have not seen this particular definition earlier, please note it down. Okay, an independent set. A set of vertices that don't intersect with each other, or that is, sorry, not adjacent with each other. Right?
Sir, here we can choose exactly one of I5, I6 and I7.
Yes. Right?
Okay, but you when you chose I1, you also told that I5, I6 and I7 together.
No. When I choose I1, I told that you can choose I4. And when you choose I1, you can choose I4 and you can choose I5.
Yes, any one of I5, I6.
Yes, any one of I5. So note that there can be multiple different independent sets, right? Like this is an independent set, I1, I4 and I5. And you have another independent set which is I3 and I5. Right? And in some sense, and I am going to use a few words that you will all kind of understand. One of them called a maximal independent set. What is a maximal independent set? An independent set that cannot be increased. Okay, like I3 and I5 is a maximal independent set. Because if you take, can you add any more vertex to this independent set?
No.
No, right? Okay. So similarly, this earlier one was also an independent set, and that was also a maximal independent set. Okay. So the maximal independent set also, there can be multiple and maximal independent set and of different sizes. One of them has maximal independent set of size 3, the other one has maximal independent set of size 2. And what you wanted to find in the problem 4.1 is a maximum independent set. Okay. So if I have to convert your problem into the problem of graph theory, it would have come to this form. Okay. Find a maximum independent set in an interval graph. Okay, so this was basically the question that you guys solved in your 4.1. Okay. Now, of course, we can ask a completely, we can ask a different question. What about this slightly more? Why do you need the interval graph? Why not ask this question? Find the maximum independent set in a graph, just in a graph. What's the problem with this question? Anybody has any idea?
Maybe empty.
Okay, independent set cannot be empty because at least one vertex you can always choose, right?
Right.
And so it is not empty. And of course, you can come up with much more non-trivial independent sets. So this is a valid question, by the way. This is not a bad question. So what I want you guys to do is the following. You go and revisit your section 4.1. Try to write your 4.1's algorithm in the graph theory way. What does this graph theory way says? Okay, fine. Now this is actually a bit complicated, I must say. So what you need here is that you need these intervals. Okay, if you remember, you were sorting based on your last the finishing time, right? So you need not only the vertices, but you also need the intervals. So if you are being given the intervals, then you can do it. But for the case of a general graph, there is no such intervals. How do you do it? Okay. So I want you guys to think about this one. I will come back to this particular problem much later on in the course. Okay. So think about this. Think about this problem. First of all, come up with an algorithm. Come up with an algorithm. And when I say I come up with an algorithm, I am not even saying that algorithm has to be fast, slow, or something. Come up with some algorithm. Okay. It can be exhaustive search. This can be exponential. It can be anything. But there is an algorithm. Find an maximum independent set in a graph. Okay. And the next thing would be to improve the runtime. So I can give you this thing that what you will realize is that you can do it in times 2 to the power n number of steps. And by improve, I mean, can you do it in something of a polynomial in n number of steps? Can you do it? Okay. Okay. Think about it. It is actually a very important question that can be asked. Now, if I have to quickly go and explain another thing, somebody was pointing out about clicks in. Okay, so I have this graph G, okay, and I have this maximum independent set of this graph G. Somebody told me that let's look at the graph complement. Okay, so G bar. Now you know what G bar is, right? G bar is basically, so if this graph is V comma E, this is V comma E bar, where E bar is, I mean, V cross V minus E, right? Set minus E, right? And somebody told about the clique. Now, what is a clique? So, you know, complete graph. Do you know a complete graph? What is a complete graph?
All the edges are there.
Huh? Yeah.
All the possible edges are.
Exactly. So, a complete graph, which is denoted as KT, is basically a set of T vertices. Okay, so like here it is a K5, but all the possible edges are there. Okay, so this is a K5. This is a complete graph. You can have K6, you can have K7, you can have K anything. So clique is the largest complete subgraph of a graph. Okay, so for example, if I have a graph which is like this, so this graph has a, if you see it, what you will see is that these 4 vertices will form a clique. Okay, a complete subgraph. Okay, you can also have something slightly lesser, like for example, these 3 vertices also forms a clique of size 3, right? So this graph contains a clique of size. So if this graph is called G, then I know that K4 is a subgraph of G and K3 is also a subgraph of G. And you can see that K5 is not a subgraph of G. Okay, so this clique of G is actually 5. Sorry, not 5. It's 4. Okay, this is it's the size of the largest graph. So what somebody claimed, if it is correct, so the maximum independent set of this graph is equal to the click number of G complement. Now, is this question correct? So this is what, if you realize, this is what somebody pointed out, claimed that for the interval graph this was the case, and I proved that this is the case. Now, so this is a typical graph theory question. Okay, that is this correct? Now I don't want to go into this immediately. I have to think a bit whether this too is correct or not. It might be correct. Might not be correct. Okay, so I will leave you guys with this question. Okay, think about it. Is this correct or not? Okay, so if this is correct, then fine, then else you have to come up with the example. I mean, if it is correct, you have to come up with a proof. If it is not, you have to come up with an example where this two is not true.
Sir?
Yeah.
Click is a number. I mean,
click is a number.
the set which will, for which we have the click will be the click of G bar will be MIS of G. But we can't write equally.
So the click, okay, good. So this click will be an MIS, that I completely agree, right? The click of G bar, that will be, those set of vertices will be a minimum, will be an independent set. MIS, I don't know, independent set of G, right? But why will be a maximum independent set? Oh, yeah, you are right. Good. Okay. Yeah, completely right. So this is actually true. Yeah, this is actually true. Prove it. Yeah, somebody gave me a proof also. So it's good. So you, yeah. Good. Okay. So any questions on this stuff? Okay, I must say that, I mean, so this course will be a bit weird because many times I have to go into this graph theory to kind of give you guys the background of graph theory, because you guys have not seen the graph theory to some level, to quite a to good depth. But that's fine. So please, I mean, you have to put in some extra effort. Okay. So this question of finding a maximum independent set in a graph. Now, okay, you can ask a similar question over here. Okay, find the click number or click or maximum click. I mean, find the max click of a graph G. Now, this is also the similar kind of question, a question that I want you guys to again come up with an algorithm. Okay. First of all, come up with an algorithm. Come up with an algorithm. Okay, again, see, this is not, it is well defined because every graph will have click of size 1, right? Because one vertex is a click of size 1. And if there is an edge, then there is a click of size 2. You know, the click of size 2 is just an edge, right? So this is a, I mean, this has a lower number, right? It is a, so it is a well-defined stuff. So first of all, come up with an algorithm, and here I am not insisting of any time complexity. And then the question is that, can you get a poly in n algorithm? Okay. Now, okay, whenever I say n, what is n? Remember that n is always size of V. Always, whenever we talk about graphs. Okay.
Sir, maximum click means?
The size of the maximum click. So click is actually not a number. Click is actually the size. This like a. So we say the graph has a click of size 4. A click is an independent. Is a complete graph which is a subset or subgraph of the graph.
Oh, but in definition, is that largest complete graph or just a complete graph?
It's the largest complete graph.
Then what is the meaning of maximum click?
So size of the largest complete graph set.
Oh, that is a number.
Yeah,
and
that's a
click
number.
is not a number. Okay.
Yeah. Yeah. Some places they use it as maximum click number. Yeah. Some places they use it max click. So. Okay. So we will certainly go over these problems at some point of time. I mean, this will be there. Okay. Fine. Okay. Now let me ask you a simple question. Let me move on a bit further. I don't think I will be able to cover whatever I wanted to cover today. But see, I have given you a graph G. And I have two vertices, U and V. And I ask, is U connected to V? What does it mean? What does this statement mean?
There exists a path from U to V.
Right. So that means, does there exist a path from U to V? Now, how do you find it? So design an algorithm. To answer the question, the answer, the above. Yeah. Can you come up with some ideas? How do you solve it?
We can try a recursive algorithm.
Okay.
So given an edge U, apply our algorithm.
No, I don't give an edge U, I gave a vertex U.
Sorry, a vertex U.
Yeah.
Apply the algorithm to all the neighbors of U.
Right, but see, then there is a problem. Okay, what is the problem? So when you apply, yeah,
the infinite stack will have
not stack or something. So you have a vertex, right? So something like, so let's look at this graph, right? I have a graph like this. Something like that. So you have a vertex U and a vertex V over here. You say that, say, okay, I want to check from U to V. So I will look at all its neighbors, which is this and this. Fine, very good. But now, right? But now when you have to apply for this vertex, then you say, oh, now I have to look for this neighbors, which is again, U is also a neighbor of V.
So that's what I was saying. We'll have to remove the infinite stack.
What do you mean by infinite stack?
As in, we won't apply recursion to the same edge again. Sorry, same vertex again.
You will not apply recursion to the same vertex again. Okay. Okay. So, I mean, it is possible that you are talking about something that you have already seen before. Can somebody say what you have seen till now? I mean, this is something that you must have done before. Okay.
DFS.
Right. You can just do a walk on the graph. You guys have seen DFS and BFS, right?
Yes.
Yeah. You remember or you don't remember? How many of you don't remember?
I don't.
Hmm?
I don't remember about this.
You don't remember?
No, sir.
No, don't be ashamed. Just tell it. I mean, I could not hear you properly also.
No, sir, I don't remember this.
So, but it was done in your discrete math course, right?
Yes, sir.
Okay. So let's see, how can we go about it? Okay. So this is basically, so these are what is called as the graph traversal algorithms. So what does graph traversal algorithm means? Graph traversal algorithms means that you start from some vertex, okay? So let's, for our purpose, let's start from U, and you want to go and visit all possible vertices in the graph. Now this is a very useful algorithm, by the way. For example, when you search in the Google, right, a particular stuff, like say you search for a particular name, say search for algorithms, right? It will output you all possible set of web pages that has the word algorithm written on it, right? Now, of course, how they rank the web pages and all, that's a different issue. But the first thing that they need to do is to go and walk along the whole web graph and find out all the places where the algorithm word is written. So that is done using some kind of a traversal algorithm. Now, as somebody pointed out, one thing that you can do is that you can basically go and visit all your neighbors, right? So if I number these vertices, I have to number these vertices. Say, let's call this number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So one option is that I will first visit 1. I start from 1. Then I visit all the neighbors. Okay. Now, how do I visit all the neighbors? I will go along a particular edge and visit 2. I'll go along a particular edge and visit 3. I'll go along a particular edge and visit 4. Okay. Now, I am not done with it, right? So I will now look at go to the first of these 3 things, which is 2, and look at all its neighbors. Now, when I look at all its neighbors, I first see that, oh, let me go to 1. Oh, see, 1 is already has been marked into red. So when I visit something, I mark something red, right? Then I said, oh, okay, fine. I don't need to visit 1. Can I visit 3? Oh no, I don't have to visit 3 because 3 is also marked red. Then we did 5. Okay, good. So I need to go to 5 and mark it red. And now 2 doesn't have any more neighbors left. Okay. Then I go to 3. Now 3 says that, okay, let me look at edge 1. No, it is already marked. Edge 4, edge 2, no, it's already marked. Edge 4 is already marked. So all its neighbors are marked. Then I look at 4. And in 4, I look at edge 1 is marked. Then so edge 3 is marked. Then, edge 6 is not marked. Okay. Now, out of this 2, 3, 4, 5, 6, what is the next vertex that I had kept, that I had looked into, was number 5. So in 5 again, I will look at all its neighbors. I will look at first, you look at neighbor 3, that is marked. Then look at neighbor 6, that is marked. Then I look at neighbor 7, okay, that is not marked. So I will go to neighbor 7 and mark it. Then I will go to 6 and I see that, okay, this is not, 6 has 2 neighbors, right? 4 and 5, and both of them are basically marked, so no issue. Then I go to, the next one is 7. 7 says that, okay, 5 is marked, fine. So nothing to be done. But then it has 8, that is not marked. 9, that is not marked. 10, that is not marked. And 11, that is not marked. All of them will be marked accordingly. And then you look at 8. Now 8 will have 7, that is already marked. And 8 and 12, that is not marked. And note that what happens here. Look at the red edges. So at this point, you can of course complete the whole algorithm like this. And the main idea is that you start from a vertex and you look at all its neighbors. Then look at the next vertex and look at all its neighbors, which are not marked, right? Then you go to another, and you slowly go over all the vertices as you have discovered. Okay, and look at the red edges. That has been red edges. Note that these red edges are the edges that was used to find a new vertex. And do you see this red edges has a special property? This red edges has a property that they are all
connected to you.
Sorry?
Connected to you.
They are connected to you, and more importantly, they don't even have a cycle. Right? Because if a vertex has been found through this edge, then it cannot be found from any other edge, right? Because they will look into it and find, oh, so see, this is 5 is already marked. So this edge will not be marked. So this gives us a tree, a subtree of the graph. Right? So if you see, what we did was we looked at all the neighbors. So we looked at all the neighbors of a vertex, and we basically wanted to keep a book track, keep a tracking about what all edges have been looked at and what edges have not been looked at. And by this way, I could have gone on over the whole thing, whole graph. Now this is called the breadth first search, or BFS. Now, first of all, what is the time complexity of this algorithm? Now note that every edge was traversed twice, right? Sorry. Every edge was traversed twice. Say, for example, the edge between 3 and 4. Once it was in 3, it looked through this edge once from 3. And once it was in 4, it was looked through this edge 4. So that means every edge was looked once, twice, right? So the total runtime, therefore, is nothing but order n. Okay, and then there was some kind of a bookkeeping and all those things. So you will see that the total runtime is order m plus n. Okay, so this is what is one way of maintaining breadth first search. Okay, now there is another way of doing the same kind of traversal. Now I have to draw the same graph. Okay. Okay. Now I start from 1 again, but this time I am not interested in looking at all the edges that goes out of 1. Instead, what I will do is that I want to quickly go as far as I can. So I will go to 2, then from 2 I will go to 3, then from 3 I will go to 4, then 4 I will go to 6, then from 6 I will, this is not a very good thing that I have done. Yeah, sorry. Maybe let's not go this way. Okay, so from 2 I go to 5, from 5 I go to 7, from 7 I go to 8, from 8 I go to 9, yeah, sorry, go to 12, from 12 I go to 9. So I basically just try to find out a new edge, new vertex, new neighbor of that vertex. At 9, I see that there is only one more vertex that has not been found out, that is not marked, and that is 7, but that's already there. So I retrace back my step. Okay, not 9, so let's come back to 9, let's come back to 12. At 12, I find that, oh, see, there is no other edge left, so I come back to 8. At 8 also, I find that there is no other edge left, so I come back to 7. Then at 7, I see that, okay, there is a 10. So I go and look at 10. Then I come back to 7. Then I go to 11. Then come back to 7 again. Then I come back to 5. Then I say that, okay, what about in 5? Does 5 has an edge? Has a vertex that has not been looked into? Yes, it has 6. So I looked at 6. Then does 6 has a vertex that has been looked into? Yes, it is 4. Does 4 have a vertex that has been looked into? Yes, it is 3. Then I come back from 3 to 4. I find that 4 doesn't have an edge. It has 1, but that has been looked in. That has been already been tagged. From 4, I come back to 6. From 6, there's no other neighbor left. They come to 5. 5 has a 3, but that has been tagged. From 3, I come back to 2. That has been also been tagged. 2 has a neighbor to 3, but that has been tagged. I come to 1, and the algorithm stops here. So here I am basically trying to go as far as I can and then come back. Again, note that this graph, that the red vertices, that was red edges, also forms a tree. Okay, but here we are traversing in a slightly different way. we are basically going down the depth as fast as we can. So that's why this is called the depth first search, DFS. And this also has the same runtime of order n plus m. Okay. Now, this is the two standard ways of traversing of the graphs, the PFS and the DFS. Now, I have not given you the pseudocodes of both DFS and BFS. So what I would ask you guys is that I will send you the link of the book where DFS and BFS has been studied or has been looked into, and please go and read them. Okay. Now BFS and DFS are very useful for various things. We will need it a lot. And not only that, we will also need certain special properties. BFS and DFS, the trees that are constructed using BFS and DFS has some nice structures. I'm sure it was done in your discrete math course, but you have to revise it once again. Okay. So, yeah, I know that it has been a bit fast, particularly if you don't remember what was done in the class, then chances are very unlikely that you will be able to get whatever was done just now. But but it will be necessary for you guys to go and revise BFS and DFS. Okay. Now the thing that possibly was not done in your class last time, but which is important, is that both BFS and DFS runs in time order n plus m, linear time in this of the input graph. Okay, so maybe I would stop now and I will let you guys go and so please read your BFS and DFS if you can before the next class, and also your section 4.4, which is the if you have section 4.4 is chapter 4.4 is something that I would like you guys to read before next class. In the next class we will do chapter 4.4. Okay. Okay, so any questions? Hello. Hello, am I audible?
Yes, sir.
Yes.
Okay. So do you guys have notes of your last discrete math course, DFS, BFS?
Sir, actually, in previous sem, we are told to read from a book, I think, and they are only said that to read the BFS and DFS just introduction, like, and not too much. Okay.
Oh,
Just what is BFS and DFS? That's and only the order of m plus n that was there, and that's not more.
Or not more than that was done?
Yes.
Okay, that's fine. For now, let's leave with that, and we will see. We have to. So you didn't do things like. Okay, so why don't I give you the links to this BFS and DFS pseudo chapters in the Kleinbach-Tordos book, and you go over this BFS and DFS in as much, because BFS and DFS is almost this ABC of algorithms. I mean, if you cannot, I mean, that is like the most important part of it. Okay, so you need to follow it. You need to learn it. So maybe we have to spend some time on this. Maybe we can have another tutorial or something like that for this BFS and DFS, various properties of BFS and DFS and so on. So yeah. So for now, I would say that please go and read this Kleinberg-Tratosch's chapter on BFS and DFS. I will give you the link to that. I mean, I think it's not 4 point. I think section 3 or something like that. And try to read chapter 4.4. So we will do this chapter 4.4 in the next class. Okay. Any questions about whatever was done in this class today? Okay, so if not, let's stop the class now. Okay.